SwayamPrabha. Digital India. Educated India.
Welcome to week 6 of the NPTEL course on Muffler Acoustics. This is the first lecture of week 6, and the entire week 6 and possibly the initial parts of week 7 will be studying a topic which is known as acoustic propagation in ducts of gradually varying cross sectional area. So, we are still considering 1D waves only, that is the waves go along the or propagate along the axis, but then now the difference is that the cross sectional area, as you can see, is varying. So, if you have a duct say of circular cross section and whose radius is something like this here, or say it is R1 here, at this point you project it, it has a much larger cross section, say R2 radius. So, the question then is that why do we need to study ducts of gradually varying cross section area, why do we need to consider wave propagation in such structures, and what is the practical importance, and those questions might be arising in any readers in any student's mind before we actually embark upon a little bit tedious derivation, because obviously here the difference is that compared to a uniform duct of a uniform cross section, and if we consider wave propagation as we have been doing in such ducts and in this duct, the associated maths even for the one dimensional test case becomes a bit complicated because of the inclusion or the presence of additional terms. So, now before I answer the question regarding the practical significance, let us first also briefly revisit or recall an important thing which is called reactive mufflers. What do reactive mufflers do? As I have probably noted in my third or fourth week's lecture, probably third week's lecture, mufflers are kind of categorized into two parts, primarily reactive mufflers and the dissipative mufflers. So, talking about reactive mufflers, they work on the principle of reflecting a significant portion of the acoustic power back upstream from where back to the source, and allowing only a limited portion of the acoustic power to propagate downstream, at least for a particular given frequency range. This may not be true for all frequencies, because in some frequencies almost the entire acoustic power is transmitted throughout downstream. So, but we will be basically focusing on the frequency range in general, in which at least some part of the acoustic power is transmitted back upstream and less amount of power is transmitted downstream. So, the whole idea is basically to reflect or reflect significant part of power back, and that is possible, we saw by the simplest possible element, that is the sudden area discontinuity, this thing. So, when a part of the wave comes here, some part is reflected back, some part is reflected back, and less amount is transmitted downstream. So, basically what happens then is that these sudden area discontinuities form the basis of the working of reactive mufflers. So, the idea is to cause a significant impedance mismatch, even for the case of extended inlet and outlet chambers that we just saw in the last lecture before we ended the last lecture. By putting 0 impedance here just at this interface of this resonator and some finite impedance here, we saw that the waves choose to go towards the path of least resistance or least impedance. So, they go in the side branch and less amount of acoustic power is transmitted towards the downstream. The entire idea behind all such things is to continuously reflect the acoustic power or divert the path of acoustic power from the main propagation direction. So, one couple of possible alternatives we saw so far was the use or the existence of sudden area discontinuity, like the one I just drew, and extensions at the inlet and outlet and so on. But what happens, the question arises that what happens when you have such a thing, the area is gradually varying. So, you see there are lots of interesting mathematical concepts we can study by considering such systems. One thing is that the area is gradually varying. So, one can imagine the radius is gradually varying, of course, with the axial distance. So, r is equal to r of z. Radius is a function of the axial distance z. So, now what it means, well, mathematically, or one would like to think, is that there are small discontinuities. The well, this technically not a discontinuity, it can be probably thought of as a duct with notional discontinuity, something like this, discontinuities which is mimicking the horn and all that. So, there are small, very infinitesimal small discontinuities that occur, or they are present along the section, and gradually from a small section we are able to get a much larger cross section. So, this is called a segmentation approach, we will talk about that in detail, but the idea of gradually varying area changes is to basically in a way kind of induce a continuous reflection of acoustic power rather than introducing a sudden impedance change. So, it is pretty interesting, because not only is it mathematically interesting, because we are allowing a continuous variation of the impedance by actually reducing or increasing the area continuously. Remember the characteristic impedance, what was the expression? It was y naught is equal to C naught by S. Now, S is a function of diameter, which again is varying with, or radius, which again is varying with the this thing. So, is C naught by pi r square. R is a function of z. It can be something like, if it is varying linearly, r z can be r naught plus alpha times z. So, alpha is a constant and z is the axial parameter. What really it means is that we are having a continuous change of impedance across the axial distance z. So, how is it affecting the wave propagation? How is the governing equation changing in the addition of such things? And we saw that the transmission loss of a simple tube, uniform tube, this was 0, because across this point and this point 1 and 2, because there was no area change, the wave, whatever the wave is propagating in this direction, there is no reflections, there are no area changes to reflect it back. However, it is quite intuitive to think that for such a thing, gradually varying area, the transmission loss, or the basically the acoustic power that is reflected back from as the wave propagates from 1 to 2, there will be some non-zero transmission loss for such a gradually varying area. Forget about introducing sudden area discontinuities like an inlet and outlet port. Even for a simple thing like a horn, 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 this is the first time I am introducing this term, horn, transmission loss across, say, the end with a smaller cross section and the one with a bigger cross section would be non-zero. So, that is because of gradually continuous reflection, small in bits and pieces, small amount of acoustic power is always reflected back. Now, and the cumulative effect shows up in the transmission loss computations. Now, apart from mathematically being very intriguing and very interesting to look at, what is the physical significance and why do we need to use it? Firstly, because in the course is on mufflers, they basically which are devices to silence the noise from IC engines, whether it is two-wheelers or four-wheelers or some other application. So, we always have limited space. It may so happen that towards the, say, suppose if you connect this to the exhaust of a IC engine. So, the exhaust gas is coming like this and it is going like this, and you introduce a sudden area change here. So, introduce something like this here. So, the real structure will obviously be much more complicated, but the point I am trying to make is that at some parts of the engine you may not have that much space, the other part you may have much larger space. So, why not get an optimal profile, and based on the space available, manufacturing constraints, the cost of fabricating such a muffler, which obviously is more than a uniform pipe. And importantly, you can do a lot of, because of the increased space available as we go towards the outlet, one would have basically, one can do a lot many things inside the muffler. So, one motivation that I would like to give you for the first time in this course is showing you a nice photograph that, of course, I got it from the internet. You can have a look at such photographs, they are widely available for different two-wheelers. Two-wheelers use things what are known as conical mufflers. So, this is exactly in sync with what we are discussing in this course, So, these are conical mufflers. The waves, it has lesser area towards the inlet pipe or the inlet side and a bit larger area towards the outlet pipe. So, the acoustic power whatever is coming here, it is spread over a larger area. So, exactly the same thing happens for horns, like I said, HORNs, horns. In fact, horns were the first applications in which the wave propagation was studied. So, basically, the horn, what it does, it has a flare, it has a certain flare, like I said, and the entire idea of horns is that what it does is basically we are trying to maximize the acoustic power distribution from its open end. So, it's basically it's a device so that if some important announcement were to be made in the ancient times or very olden days, and even in modern times we have lots of such devices for public addressing systems and all that. So, the idea of the basic fundamental underlying this is to at the outlet side or where the waves are going propagating to the atmosphere, the pressure should be, the acoustic pressure should be in phase with the particle velocity. So, even at the lower frequency, lower end of the useful frequency spectrum, the pressure, acoustic pressure tilde, P tilde and U tilde, that is U tilde is the acoustic particle velocity along the axis of the duct. So, P and U are in sync or are nearly in the same phase. So, if that is happening, if this condition is met, then maximum amount of acoustic power can be transmitted towards the atmosphere, and it will be more effective in radiating sound. So, the horn basically flares to a larger mouth, that is this part, in such a manner that the shape of the wave fronts that propagate here, they are not substantially altered. The sound energy is radiated from the horn mouth with pressure which is substantially in phase with the particle velocity. When all these conditions are met, maximum power is transmitted, like I said. And another thing that I want to quickly add is that what a flare does is basically split or gradually reduce the intensity of the waves, because the same acoustic power is distributed over a significantly larger area. So, while the total acoustic power is conserved, the intensity reduces because the area over which it is spread has increased. So, that is one important feature of a horn, to basically create a equally energetic acoustic pulse or acoustic wave, but of lower pressure, amplitude and lower velocity, because it is distributed over a larger area. So, now with this background, what we will do, probably horns obviously were a classical topic that was discussed. With this, we will go to the classical equation which governs the propagation of one dimensional waves. So, let me draw a fresh figure, let me draw it a completely new figure, something like this is the horn, and this is the axis. Okay. So, the waves basically they propagate along the axis. So, the waves propagate along the axis, along the direction that depends only on the z coordinate. So, the waves are essentially 1D in nature. So, we are basically going to have a look at the corresponding equations that govern the wave propagations in a greater detail, and see how we get an extra additional term just because we have a flare or the gradually varying cross section area. So, interestingly, for a special case of a conical horn, you see that the spherical wave equation, just like you have one dimensional equation for a uniform tube, we have spherical wave equation, one dimensional spherical wave equation. There is no dependence on theta and phi coordinates, that is, there is only dependence of radius r from the origin. So, such equations can also govern spherical waves in conical pipes. So, the form of the one dimensional spherical wave equation is the same as that of the equation obtained by the Webster's horn equation for a conical pipe. So, that is a special case, we will soon come to it. We will do some special cases like exponential horns and conical horns, and few cases for which the analytical solutions are well known, and then go for a more advanced mathematical modeling in this week, like segmentation approach and possibly matricent approach, perhaps solve a few problems for the transmission loss, and then probably end up this week's or this particular topic's presentation by introducing things like some perforated elements, although the detailed analysis will be done in the later ensuing weeks lectures. So, let us begin now with the thing what is known as Webster's horn equation. So, basically for a gradually varying area duct. So, if P tilde is still the acoustic pressure. So, we will soon see that after a little bit tedious derivation, the form that we obtain would be the following. Well, if you consider a wave equation, will be like this, the difference being that this will be replaced here by del well, we will see how we get to this equation. This will be our objective, and S here can be any function of x or z, you see that. So, obviously, when S is constant, that is if you have a uniform pipe, what is S? S, this is a constant, say alpha, some constant. So, d dx of S is 0. So, then in so because this term is 0, this one, the entire term goes away and we get the well known equation for the one dimensional tube. So, that is a special case, but right now, well, our focus should be to derive this equation, which we will do in a while. So, what we will do now is that we will consider a control volume, something like this, which is kind of representative of the duct of gradually varying cross section area. We are basically considering a small chunk of element here, but we kind of zooming it, we kind of magnifying it to get this part. And so, this is a small volume actually, and this goes on like this. Now, there will be definitely some amount of fluid that will be entering within the control volume. So, I will write it CV, control volume, and there will be some volume of fluid that will be entering. So, rho u s is the at x. So, this is, let us say this is, this section is x, this is x plus delta x. So, density times velocity, which is normal to the cross sectional area, times the cross section area at x. Remember, S is a function of x, and now this is the mass flow in, and what is the mass flow out? Mass flow out, that is rho u s into x plus delta x. Okay. So, this is what it is. So, what is net difference? Net difference of the inflow and the outflow mass is given by rho u s at x evaluated at x minus rho u s evaluated at x plus delta x, that is the net difference. So, this is the net mass that is being added to the elemental volume or the control volume. So, this we can relate it to the temporal change. So, what is the volume of this element? S times delta x over the small length delta x. Okay. So, S into delta x is the volume multiplied by density will give you the mass. So, the temporal change of mass is nothing but del del T of del T of rho S into delta x. So, that is your equation that needs to be simplified. So, temporal change of mass within the control volume is the net difference of the mass that enters the control volume and the one that leaves the control volume. Okay. Let us call this equation 1. Let us simplify equation 1. So, remember S is not a function of time, and however, delta t can be a function of time. So, what we do basically is that we take this and divide throughout by delta x. So, rho u s at x minus rho u s at x plus delta x divided by delta x. Now, we take the limit when delta x is tending to 0, that is this element that we saw here it is basically getting smaller. We basically consider a very small element, that is the length is very small. So, limit delta x is tending to 0. This means that we can write the right hand side as, let us first rearrange this term at x plus delta x minus rho u s at x divide by delta x. So, this we can write it like rho u s with derivative with respect to x. So, suffix x means derivative with respect to x. So, what you get is basically s times del t of rho is equal to minus this thing, or in other words what we can do is that just rearrange a few terms here and there. This thing where s Sx and now let us open the terms within the bracket. So, when we do that we get this thing plus your s times, I would still prefer putting all the terms within the bracket. So, we get this part. So, now we can clearly see that this becomes del t of rho plus your 1 by s into d dx of your s times rho u plus rho u x is equal to 0, or in other words, so this happens because s here and s here gets cancelled. So, now when you write this above equation in even more compact form, we can write it as natural logarithm of s x times rho u plus so, we get equation number let us say 2. So, one corollary that can be easily seen from this equation 2 is that when s is equal to s x is equal to constant as we saw, then of course, this term goes away, what I have been talking about in the last class. So, we get back your old continuity equation for a uniform duct. But in general case for a gradually varying area duct, this will not be 0 because s is by definition a function of the axial distance x. Okay. Note again here that waves in a gradually varying area duct are never one dimensional, they are always, at least they will be 2 dimensional in the sense that they will have a motion along the z axis or the x axis, I am sorry, and there will be some component along the r axis. So, but these area changes are very gradual, or I would say the discontinuities are only notional if we talk in terms of segmentation approach, what I talked about. So, then because these area changes are so small, it does not really matter if even if there is a small transverse component, they are very small compared to the axial component. So, we will focus only on the 1D part, that is the axial part. So, anyhow this was the equation number 2. Let me circle this with inbox this with red color. Now, what do we need to worry about? We need to worry about the momentum equation. This was the continuity equation and momentum equation. So, it will turn out that momentum equation for a duct of gradually varying area section is the same as the momentum equation for a duct with a uniform cross section. However, we will again resort back to the control volume approach, and this in fact is this even more needed in for deriving the momentum equation. So, before that let us first understand a couple of things, that this is x, this is x plus delta x, this entire thing is length is x. Now, what is clearly the area of the duct is increasing. This is say S of x plus delta x, this is S x. What is your change that we will need it, which will be evident very soon. Why do we need it? The change is basically this part. Let me denote this by S delta perpendicular. Simply subtract this entire bit from this smaller bit, you get the change in the cross sectional area. So, we need to identify the forces that act on each of the face. We need to identify the force that acts on the face here and the forces that act here. So, now momentum flow, force due to momentum is basically rho u square s at x, but then there is a fluid flow that is going in this direction, rho u square s at x plus delta x. Now, let me reiterate again, if some of you have missed the first few lectures, that what is the unit of rho u s? It is kg by meter cube by meter by second into meter square, and if you further add meter by second. So, this all these gets cancelled, you are eventually left with kg by meter by second square. I am just trying to verify the dimensionality of this term. This term indeed has a dimensions of force. So, it is something like rho u s. So, that is your mass per second into the velocity. So, that will give you the force. So, it is not just mass, it is mass per second times the velocity. So, it has the units of force dimension wise. So, you get all these things. Basically, this works out to be the force that acts on the face on the left hand side, and this is the equal, and this is the force that acts due to the flux that is leaving on the other side, due to the flux that is leaving here, and we need to take a difference of the forces due to these fluxes, and that is how we will probably get the terms in the momentum equation. Now, what we basically need is the other force, obviously the pressure force, that is P. So, that is P times cross section area at x, that is the force that acts here, but then there is equal opposite force. I will not say equal, but there is an opposite force P s into x plus delta x. That was also our case when we saw a duct with a uniform cross section area, but now we need to have an additional term, that is this. Now, remember, now here comes the crucial part of the derivation. This is the gradually varying flare. So, this was the projected, let me project this area. So, it will overlap with this term, do not mind. This was like this and this part is like this. So, basically we are looking at the annular area, what is the difference. So, when we consider delta s perpendicular, what we actually get is s plus x plus delta x minus s of x, we get this term. Now, this difference of the area times your the force that acts, let us say we consider the force that acts somewhere in the middle, we consider the force that acts on the middle, that is P of x plus delta x by 2. We consider this part. Okay. So, what do we do now? Basically, what we do is that there is an additional force, additional term, and that is delta x perpendicular times P evaluated at x plus delta x by 2. So, this is an approximation. So, what is the net body forces that are acting on the control volume? Body forces that act here and here plus your body force that acts due to delta s perpendicular is nothing but minus P s into x plus delta x plus delta s perpendicular times P evaluated at x plus delta x by 2. Okay, we get this. Now, we recognize the things that delta s was this one, and P x plus delta x by 2 is nothing but P, we use a Taylor series approximation and get the following. So, we get this term, and then possibly what we do is sort of do some simplifications. we would like to do some simplifications and substitute all this thing in here to get P s x minus P s at x plus delta x, and we substitute. Let us first retain this part, but then once we substitute this part in here and simplify P x plus P dash x into delta x by 2, and sort of carry out our regular algebra. So, we will get, after a little bit of algebraic simplifications, the following term: P s into x plus delta x minus P of x plus delta x times s of x plus delta x plus delta x by 2 times delta s perpendicular times P dash x. We get this. So, this is the term that arises due to the surface forces, basically surface forces that act on the different surfaces of the control volume. So, what is the other force that acts? Basically, it is your rho u square s multiplied by x minus rho u square s multiplied by x plus delta x. This is the net difference of the force that acts on the control volume in here. Okay. So, we get this. This is the, let us say, the force due to the momentum. So, let me also box it, and what we get now, the sum of F s plus F m should be equal to the time rate of change of the momentum. So, you see rho times s into delta x was the mass present in the control volume, in the shaded control volume, isn't it? Rho times s into delta x. If you multiply this by u, that gives you momentum. So, you take a temporal derivative of this. So, after a little bit of simplifications, we can of course take s out of the derivative sign, because it is not a function of time, and delta x we divide throughout by delta x, just like we did for the continuity equation. Once we do that and then simplify s, rho u square s into x plus delta x divide by delta x, and I probably need to hurry a bit. So, I am just writing out certain terms. You can work out some simplifications on your own. Delta x and plus half times delta s perpendicular P dash x. And now, in the limit delta x tends to 0, what do we get? We will get, after some simplification, s times rho u t is equal to minus rho u square times x s minus s times p x. Okay. What we can possibly do is that use the other equation. Now, use the continuity equation, given by rho t plus rho u log s x plus rho u x is equal to 0. We need to use this, expand this guy out and keep this aside, expand this out. So, let us very quickly get about doing it. So, here you get your u and rho and t. Okay. We transpose these terms on the right hand side and get rho u times s whole evaluated at x times u plus u x into rho u s, and here of course we get your s times p x. Now, if we recall, actually this was a simplified equation. What we probably could also use is that the particular form rho u s into x is equal to 0. The other term that I wrote was expanded out version of this. So, why am I telling you this? Because now we can clearly identify terms, this term and the other term is your this term. So, basically we can take this guy, take this u guy common, and then your this term and this term will cancel out because the sum of these terms is 0 as we saw. So, what are we left with? We are left with only this term and this term, is not it? Actually, there would be plus sign here because I am kind of transposing it on this side, and this will be equal to 0. Let us nicely write it down all the things, but actually we can also divide throughout by s, because s is nowhere there in the derivative part. So, the simplified part is rho times, I would say, u t plus u into u x plus p x is equal to 0. That is rho times del t of u plus u into del x of u plus del p of. So, p is the total pressure, mind you. So, this is your momentum equation, which is the same that we got for the duct, that is for the duct with a uniform cross section area. Now, obviously, if you put u to be u naught plus u tilde, we can actually get the thing for a mean flow, but we will, one thing that I kind of forgot to mention is that we are just considering a stationary medium here, we are not considering mean flow. So, basically u will become your u tilde, what it would mean is that this equation will further simplify to the form where this is this thing plus your p tilde, because remember p is equal to p naught plus p tilde, and we are not assuming any gradients of the pressure as we go across the axial direction, and we will eventually be left with this equation, the linearized one. And similarly, we can get a linearized version of the continuity equation and isentropicity relation. So, what we will do is that we will stop here. It is already an extended lecture, I would say. Thanks a lot, stay tuned.